Hello everybody, I'll be recording this video while having a bit of a cold, so hopefully I won't make too big of an impact in how good this will be. Anyways, this video is about some tips about how to write your ESS IA report. This is for of course, for the new syllabus, since I'm recording this in 2026. I'm gonna be using the official ESS assessment criteria and the teacher support material from the IB, plus my own experience as a teacher in ESS and my scientific background. So the first thing we'll look at here is going to be the start of your report. Now, the structure of the report can be kind of anything, really. I mean, it should be somewhat specific to your field, but there's no, like, IB says this is how you're supposed to do it. They do say this, however, that at the very start of your report, you need to put the title of your IA, you need to put your IB candidate code, which you get in DB2. And if you have collaborators, you also need to specify the candidate codes of all these people as well. And then you need to write out your word count. And this information may be on a separate title page, but it's not necessary. It can just be at the first half of the first page. It doesn't really matter. Your maximum word count is 3,000 words, and that excludes words that you put in charts and diagrams, but not if you make a table full of text. Then those will be used for the word count. However, if you make a normal table of data and it has headings and stuff, that doesn't apply, or that is not used. Any equations, formula, oh my god, equation twice there, but equation, formula, those are not in there. Any calculations, I think, would be what I actually wanted to put as the third word. Citations in your text, they're not in the word count. The reference list or the bibliography at the end, that's not in the word count, and the headers are not in the word count. Alright. I will, however, even though the IB doesn't have any specific suggestion for the structure, I do, and that's because of my scientific background, I guess. So I've always been taught to write with the IMRAD disposition, and that works really well, I think. So let's look what that looks like. It has 4 main sections. The first section is going to be introduction, so it's ahead of the introduction you write your title and all that. But the introduction is the first main heading of the body of text in your report. The main points of the introduction is to give the background information and put everything, the relevant context of your study and your aims. The next comes the materials and methods, where you describe what you did, so someone else can understand what you've done and also reproduce your results. Then you have the results section, and that describes the data that you got. And then finally, the discussion is basically putting the data back together with your aims and hypotheses that you had in your introduction, and trying to explain what your results mean and evaluating your experiment. So now I'm gonna, after this, now that we have the general idea of how the report should be structured, according to my opinion at least, we'll go through the different parts here, the introduction, materials and methods, and results and discussion step by step. And we'll look at the assessment criteria that are relevant for these. So, introduction. Introduction will be assessing 2 criteria. So the first one is criterion A. Sorry, I was about to say 1. Criterion A. And that is how well you describe the context of your experiment. So that's going to be about your environmental issue. So your the ESS guide is very specific that you need to link everything here to one specific environmental issue. So the environmental issues that could be used here include, for examples, climate change, water pollution, soil pollution, loss of soil fertility, air pollution, whatever, right? Eutrophication. These are the environmental issues, or some examples of environmental issues you can look at. And the criteria here, or criterion, is about describing or explaining the local or global environmental topic or issue with sufficient background to support the research question. And then the second strand here is about stating a focused research question that addresses the chosen environmental topic. And you can see also the difference here for the 1 to 2 mark or 3 to 4 mark mark band, saying that there's a lack of focus or it's not linked to the chosen environmental topic or issue. That's going to make the research question more poor, whereas that of course has to be linked and is focused then to get the higher marks. Now let's look at what for the first strand here, the environmental issue. We have the words describe and explain. Those words mean something very specific. When it comes to IB, we need to look at the command terms to see what that is. So the difference between describe and explain is that describe says that we give a detailed account, and explain says that we give a detailed account and we include all reasons or causes. All right. I'm going to be trying to put these suggestions in relation to one specific experiment or an example. But let's see what we can do here. So some tips then to do what these assessment criteria demand. And the first thing I would do for the introduction is to start broadly about your environmental issue. State clearly which environmental issue you're talking about. You may want to include some relevance, describing the relevance that it has for both societies and ecosystems, since this course is environmental systems and societies. So that's a pretty nice thing. Give like the big picture, describe the relevance. For example, climate change is one of the largest problems human societies have faced, blah, 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 blah. And give references to these statements. If you say that it's relevant for human societies, then, for example, food production, give a reference for this, like the IPCC reports or whatever. Then you should, of course, to get to the explain, you need to give the causes for the issue. So climate change, of course, caused by increase in concentration of greenhouse gases in the atmosphere from humans mainly burning fossil fuels. Then, of course, then you should give consequences of the issue. Would also, in my opinion, be nice. This would either be potentially, in my opinion, also kind of lean into the explain statement, but it's going to be important to give like the relevance of the issue, but also probably leading into the research question that you have. Because now you can start shifting the focus of talking about this topic in the broad sense and start narrowing it down towards the research question that you have, the aims that you're trying to reach. So then this whole text then will start narrowing down to your specific research question. Now the research question should be seen as some kind of summary of what you're trying to do and summary of your experiment. What the teacher support material says about the research question is that it does not have to have the phrasing of a question, so it doesn't have to end with a question mark. But it must include your independent variable and your dependent variable and your, in my opinion, the study system or species. And to make it focused, you need to include ranges of the independent variable and the unit, and the dependent variable with the unit as well. Those things will make it focused. So let's assume here for the example I said I would link this or put this in context with one example. I'm gonna use a lab experiment where we've grown algae in different temperatures. So then climate change was our environmental issue. So here, my background information should be giving context to what independent variable I chose. So if we talk about climate change, some consequences of climate change, of course, is that we have warmer water temperatures, but we also have higher pH or lower pH values of the water. So those could be independent variables that are linked to my environmental issue. So you basically need to motivate, or your background information kind of should naturally justify the choice of independent variable. And then we have the dependent variable should also be relevant to your environmental issue and should be kind of linked to those consequences we talked about. So if we once again talk about our example about algae in different water temperatures, then the density or the growth of the algae would be a relevant dependent variable, and a unit of that would be, for example, number of cells per milliliter or something like that. Or if we're using spectrophotometric ways of estimating the algae, it would be potentially the absorbance of algae cultures. And the research question is placed at the end of the experiment. And that could be the very end, the end of the introduction, and that could be the end of the whole introduction section. The teacher support material says that you may state a hypothesis at the end of your introduction, but it does not contribute to your grade in any way, but it could be useful for the way your prose and how you write, basically. If you do put a hypothesis at the end of the introduction, you should not put a null hypothesis. Null hypotheses are reserved for the statistical tests that you may or may not be using. For example, an example hypothesis here would be that the increased temperatures inhibit growth of algae, and then you would predict from that that the higher temperatures will have lower algae density or something like that. Okay, is there anything that I feel like I've forgotten? We talked about the research question. We talked about the background information. Sources are super important for your background. So basically all statements need to be followed by some source. I would suggest strong reports have somewhere around 5-10 sources, I think, for the background information. So that's something to maybe look into. Let's go on. Right, and we already said that. Shboom! Next part here, which could be in the introduction, is going to be criterion B, which is the strategy. So if you look here at the mark bands here, or the mark strands, it says that we need to state or describe an existing strategy to address the environmental issue linked to the research question. So the environmental issue we should state and describe some strategy to address it. That could be, for example, this is a criterion that many students misunderstand. They think it's something to do with the strategy of their method. It does not have to do anything with that at all. So it's basically, you should look more broadly. So for example, since I talked about climate change, a strategy to deal with climate change is basically either any mitigation strategy or any adaptation strategy. Though if you don't know what those are, you will get to see those when you come to that chapter in the syllabus. But adaptation means that is how we change society to deal with the consequences of an environmental issue, and mitigation is basically reducing the environmental issue in the first place. So a mitigation strategy for climate change is carbon tax, for example, taxing things that release carbon. Then you need to describe that. So basically, what does carbon tax strategy mean? What are the consequences of it, and so on? And use here also research to support your statement. So sources once again. Then you need to explain how people with different perspectives view this strategy. The outcomes of it, so if there's a carbon tax, that will make certain things more expensive. For example, gasoline will be more expensive, and that will make some people very angry, and that will lead to a conflict. Other people will think this is the best idea ever, and think that it's great. And that these conflicts will also impact the success of the strategy. So if people don't like the strategy, that could, of course, lead to it being lead to protests and people not following this. So basically, perspectives here can be many things. You see that it's economic perspectives. It could be social, so rich versus poor. Social could be different communities. It could be rural, urban. Political or environmental perspectives. So environmental perspectives are those I think that most of you will be familiar with. Those are the technocentric, ecocentric, and so on. So basically, they're basically here, in my opinion, doing a little bit of exam work here. They're asking you to kind of be able to put these, put the concept of perspectives into your report. So it has nothing. These strategies can be completely kind of unrelated to the exact research question that you have and the project that you have, but only be linked to your environmental issue. So they can be quite. So for me, these strategy criterion is kind of shoehorned into the report. But this is what it is, and shouldn't be too nasty. I think maybe half a page or something like that could be developed to the strategy section. It can be placed anywhere. I feel like the somewhere in a half point of the introduction kind of, or in the introduction kind of makes sense, or between the introduction and the materials and methods if you want to make a separate heading for it. A common mistake is also that students write about many different strategies. So focus on one specific strategy. So take one strategy that you can find tensions and conflicts between people. That's what you need to really look for. The description of the strategy and finding sources for that will be easy, but finding something where you also find sources for tensions and conflicts, that's going to be more difficult, I think. And you need to end this section with your own viewpoint as well. That's what they want to, even though it's not necessarily said here in the assessment criterion. That's what they stress in the teacher support material. So please add your little own viewpoint at the end as well. And discussing, let's see, and it says in the teacher support material that you should discuss how the tensions impact the outcome. So discuss means that you offer a considered and balanced review that includes a range of arguments, factors, or hypotheses. So that's what that means. All right, let's continue. Oi, that went really fast. The materials and methods section, that will assess one criterion, and that's criterion C. So this section should, like I said before, describe what you did, how you performed your experiment. This means that you need to write everything here in past tense, and you don't use the imperative form. I've seen a lot of students do this, where they say, do this and then do that. No, it's not a recipe, it's a description of what you did. And the idea to score high, it needs to be repeatable, and the description needs to make it repeatable, and the method should allow to the collection of sufficient data to answer the research question. Now, my tip for writing this is to start with a general outline of your study. So basically give people an idea of what the experiment looked like, so they can then understand the specific details. I feel like a lot of students provide too little information beforehand and then rely on a step-by-step guide later, which provides lots of detail, but then you don't have enough you don't have a general picture in your head when you're reading this, what these things are. So no context for them. So I like having a general outline first of what you're doing. This outline could be so detailed that you can not even have one of those step-by-step list of your procedure later, and it can also have enough information about the instruments you used to omit a materials list. So everything that you would put in a material list, you can put in the description here as well. So in our example of the algae grown in different temperatures, it would be I would suggest maybe something like this. A simple lab experiment was used in which algae were cultured in flasks with nutrient medium, and they were placed in incubators set to the individual temperatures. It's possible here to motivate the range of your independent variable here. You can also use previous studies to do this. That's research studies that you find online, or you could have done pilot experiments to kind of determine the range of your independent variable. That will make it a bit stronger. Otherwise, you can justify it other ways as well, but that if it doesn't have a strong motivation, that may score a bit lower. And then you should also write how you got your dependent variable, and that's going to be important as well. So in our case, for example, we could measure algae density in two ways, either using a microscope and a counting chamber, or a spectrophotometer, which would measure how turbid the water is at a specific wavelength. So, for example, the growth of the algae was estimated by taking samples of the algae cultures and measuring their absorbance at X wavelength, and comparing the values at the start of the experiment to after X number of days to estimate growth, and the growth would be the change in absorbance of the algae cultures. If you do not motivate your species, study species or field site or whatever it is in the introduction strongly, you can also do it here. So try to describe why your study species is relevant for the environmental issue that you covered. If it's a normal lab species, that could be relevant. If it's a freshwater species and you're looking at ocean acidification, that would probably be a bad idea. But basically, the consequences and issues that you talk about should be relevant for the species that you choose, or it should be a relevant model for some way. You can use illustrations and photos to show your experimental design. There's something called BioRender, a website where you can make a free account and make 5 illustrations, and these look very professional. There may be other similar applications that you can use as well. You should also describe and motivate how many replicates, that is the number of data points that you have of the same IV level. So in my case, temperature here, how many replicates of the same temperature or dependent samples have I taken for each of those, and that it relates to reliability is something that could be useful. For example, each data point will have variation associated with it, uncertainty and errors. Getting many data points and calculating an average for them will be more reliable than having just one data point for each IV level. Also, that having replicates allow for statistical testing, which will deal with uncertainty and increase validity and reliability, will also be strong ways of motivating your number of replicates. These terms that I'm talking about now, reliability, validity, and so on, they will come back later when we talk about evaluation. The general rule for IB is that you have is the 5x5 rule. That means that you have 5 levels of your independent variable and 5 replicates in each. That gives you total 25 data points. And that relates to the second mark strand about sufficient data. If you instead compare just 2 groups, for example, 2 groups of students or something like that, then you need to have at least 20 data points, so 10 in each group, I would say, would be useful. For example, if you, in my case, potentially study the albedo and melting of ice, then you need to have 10 samples for those that were manipulated and those were not manipulated, for example, by placing shade over them or increasing albedo by making the surface wider or something like that. So the manipulated should be 10 data points and a non-manipulated should be, the control group should have 10 data points. If you do some kind of correlation analysis, they suggest that you have around 30 data points in total, so that's kind of close to this 25 data points by the 5x5 rule. If your method is particularly difficult and time-consuming, they accept fewer data points. However, conversely, if your method is very easy to perform and you should be able to get many data points, like, for example, having seeds and seedlings and checking germination, that they expect you to more. Or if you do a survey and just send out a survey to your school, then you need to have at least 30 data points or candidates per group. Now, when it comes to making your method or description of your method repeatable, you need to have, of course, sufficient detail. Either, like I said, here in the general outline of or description of the experiment, or in your step-by-step procedure. For our example with the algae, you want to describe, for example, which type of water did you use to culture your algae? Do you use distilled water? Do you use aquarium water? Do you use tap water? Do I use pond water? Whatever. Which kind of chemicals did I use? What's the nutrient that I use? What's the brand? Which purity was it? Which manufacturer for my my equipment? You need to also give the brand, the model, and the uncertainty associated with it. If you to get a specific concentration of a pollutant, for example, copper sulfate or so on, you need to describe a method or how you calculate the specific mass of that chemical that you used to get that specific concentration that you wanted of specifically copper in the copper sulfate solution or molecules that you chose. How did you weigh them? Which scales did you use? What's the uncertainty of the scales, and so on. If we did the algae and we wanted to do the spectrophotometer, or if we did a microscopy-based method, you may want to need to stir the solutions before taking samples, so you have nice homogeneous samples and so on. So that's going to be important as well. It's going to be important as well to talk about control variables, and that's going to relate later on as well to your evaluation. Let's see where we are here. Yeah, that one we already had. Sorry for being a little bit confused there, but yeah, we already managed this. Solutions, how you mix them. Choice of field site, how it represents your independent variable or study species. Yep, those things we already mentioned. So, but now you see them as well in case you're not really listening. And repetition is the mama of all learning, isn't it? Right, your dependent variable, number of replicates. Oh my god, how silly I'm not for having those earlier. There we go. Cool. Now, this is where I wanted to be. You need to describe how you set up your control variables. So control variables are any variables that could affect your dependent variable, and that you then, of course, need to make sure are the same for all your experimental groups in the your experimental groups, so they're not varying between them. Otherwise, that will impact your conclusion, and that impacts your evaluation. Now, I would put those in a separate little section potentially, or subsection of the methods, but I wouldn't want you to put headers, for example, apart from the introduction, materials and methods, results, and so on. So just have their own paragraph. You could use something, statement such as like this, to increase the reliability and validity of the experiment. I controlled these control variables. So basically, for each of those control variables, you need to state which variable it is and use correct SI units and for these. So for example, if it's water, state volume or type of water, not number of algae, then it's like concentration of algae, or amount of water. Volume of water is what you want to use. So be sure that you use those SI units. Justify why you control them. So basically describe why you need to control for these. So how do they impact your experiment? So in our case, nutrients impact the growth of algae as well, right? Temperatures are independent variables, so we don't need to state that, but light does. So describe why light is important. It affects photosynthesis, that it affects how much nutrients or how much organic or the food that the algae has available to it, so that it can use to grow. So basically, and then you write, how did I control these specific variables? So how did I expose my algae to light? Ideally, you want to measure the light intensity as well. That's the highest order of control. Not just saying I did it this way and it's the same for everything. That's fair and that's cool, but to make it really repeatable, you need to you need to also measure them. Otherwise, placing them in the window in Sweden, it's very different from placing them in the window at an equatorial country, especially in northern winters. So the main idea is, of course, to have fair comparisons, that these control variables don't kind of lead to some kind of bias, but it's going to be important to get it repeatable, to reach the higher levels here, to describe exactly how to control them. This can be done either in plain text, or it can be done in a table, and this kind of table will contribute to word count. So I would then, if you do a table, I would use the first column for the variable, second column for the motivation for why you chose to control this variable, and the third for how you controlled it. And if you decide to use a material list, it could look something like this. It needs to include the equipment you use and be specific so that it can be repeated by someone else. Uncertainties, models, brands, volumes, everything. So here I have an example from one of my students from before. Not everything here is perfect, but it's like, okay, they grew these duckweed in petri dishes. So they had which species they chose. Of course, that should be potentially also measured somewhere else, but whatever. Lemna minor, or in our case, maybe an algae, the specific algae culture. You can, of course, describe how that base stock culture that you used was kind of treated before you got your hands on it. 1 liter of distilled water, a waterproof digital probe, stating here what the brand was, and the model, and the uncertainties in it. That's very nice. That they used sodium hydroxide as solution, and then stating the concentration of it. This is a chemical unit that we don't need to necessarily have, but it's very nice if you do. Registers and so on, measuring cylinders, and they're measuring uncertainty, the nutrients they use to grow these ones in, and the brand and of that. That's pretty nice. The step-by-step procedure, which you then can omit if you have a really nice description, also from the same example here. So have this detailed enough so someone can repeat your experiment and get the same results. Is the ideal here, of course. That it should have enough detail. Now, usually in these ones, here they describe how the dependent variable was estimated. Pictures were taken, and the image was labeled according to using Adobe Photoshop counting tool, and they have a little figure for it, and that's pretty nice. I think this is slightly too vague for how you got the dependent variable, and I think the description of how you got your dependent variable is usually, or often I've seen something that you do a little bit too vaguely, or students do a little bit too vaguely. So be sure that you have that either here or in your description quite of the method. If you do that in prose very clearly, that's going to be very important. Now we can leave criterion C and the method section and go into results section. Results section will also just look at one specific criterion, and that's criterion D. You should here in your results section describe your results, your methods of processing, and observed pattern. So not processes, processing and observed patterns. Now the mark bands for this criterion are here. Basically, it has to do with the communication of raw and processed data is clear and detailed. Techniques that you use to process the raw data lead to findings that fully address the research question, and the raw data is processed correctly. So basically, that to communicate your data correctly, that you use relevant techniques, and that you do it correctly. That's the main idea here. The most common mistake I see in this section is that students just put the tables and figures in the report with very little describing text. My overall suggestion is to guide the reader with the text and then support your text with tables and figures instead, and not the other way around. So, and this is also one of the sections that is easiest to write first, actually. So, in my scientific background, this is a tip I was given by many of my supervisors to write the results section first, and then basically build results and materials and methods first, and then introduction and material and discussion are basically the last two things that you write. That does, of course, involve that you have to kind of have a good idea about your introduction already before, like the environmental issue and so on. But it can be a good way to get the ball rolling, and to actually, if you have like writer's block or something like that. If you have long culturing time, for example, of course you can then write materials and methods and introduction first instead. For example, here I would culture the algae for a week, then I have a week that I can write about the other things first, because I can't do anything about the results. Also, this to get this kind of idea about the text being the main guide, I would actually suggest, if you make tables and figures, which you should do, of course, you should be able to remove those from the results section and have sufficient detail in your text that a reader would still understand the conclusion that you draw later. So I'll try to make that clear in what level of detail you need to have. Okay, so start the whole section with text. Describe what the data you have. I would suggest starting with qualitative data. Photos are really good here. So let's say I cultured my algae. I would then place those flasks of algae culture on a table and take a picture of them if I can see that there's a difference in how dense or how green or whatever color the algae is those different flasks are. So that would give us a visual appreciation of the results already. So that was very nice, but make sure those photos are clear, not just, that you both can understand which flask is what, but it also has that they're big enough to see in the picture and so on. Some kind of text that you can use would also be kind of repeating potentially the method as well. So, for example, I could state something like this. In this experiment, algae were cultured in different temperatures. After a week, the culture showed a marked difference in the apparent color, and you show a photo. The way to do a citation would be writing those words and putting a bracket inside the bracket. You make the reference to which figure they should be looking at. And saying something like the cultures grown in higher concentration showed a noticeably paler color. Quantitative data was included absorbance values of these different cultures, and at the start of the experiment, the range of values was from X to Y, and then, for example, 0.05 to 0.89. That will be actually at the end of the experiment. And then refer to where a reader can see this. So this is how that would look, for example, in a text. Now, you don't need to then write about every individual data point. So now we're talking about the level of detail you should have here in the text. So you don't have to write about every individual data point, but you should maybe talk about ranges, averages, and so on. So we have now this kind of general description of the data, the range of the data. Okay, let's and we refer to a table. So we need to report our data in tables, and they're really good for showing both your quantitative data and your process data. But don't just put the tables there. And so the tables and figures are not the leaders of, or are not the way that you should lead your description of the results. I have had a lot of students write like, as you can see in table 1, or table 1 shows. Like, I think it's better to just, or as you can see in table 1, just write what the data is in words and refer them. They support your words, and your words aren't supporting the tables. It's the other way around. To make tables then, so we need to make nice looking tables. I have a separate video for that, which I can show you, but or that you I can link in the description. But this is one of my students' tables, so I'll use that because it's really nice. Okay, I recommend you do your tables in Microsoft Word because it makes much neater tables than I've ever gotten Google Documents to ever do. Need to use headings for variables and units on the first row or rows. So here the independent variable is on the first column, and then there's a number of columns that instead have the dependent variable unit and many different replicates, and at the end we have the processed data. So each new column here represents one replicate. So in this case there were 8 replicates for every individual level of the independent variable. So every new row shows a new level of the independent variable here. Above the table, you should have a table legend that should include the number of the table. So whenever in the text I say table 3, they should be able to easily find that by having the number there. And then you should write a descriptive legend. This is a very nice descriptive legend. It's basically shows the zones of inhibition, the dependent variable of the E. coli. Oh, here they didn't use the small c. But basically which species it is. By various Manuka honey solution concentrations, an independent variable after 24 hours of incubation. Or it could also, of course, be then having a separate table for before incubation. So not in this case, of course. But basically, the table and the table legend together make up the kind of graphical unit here. And they should be, the information in the legend plus the headings and so on should be sufficient to tell us kind of everything we need to know. Shouldn't have to read anything else, but just look at the table and the heading to kind of understand what this table represents. The only thing this student does not have is the uncertainty that we have for the dependent variable here. That's something I would definitely encourage you to have, or that you should have up here. This student had a slightly different way of doing this, so that it didn't really give a nice uncertainty that we can use. Then for the analysis, here we have the processing. So you have the mean and the standard deviation. So you should describe why you calculate the means and the standard deviation, and how you calculate them. So the teacher's word material says that you don't really need to have an example calculation of showing here that these 8 values, like having a sample calculation of all these values summed together divided by 8 to give this value. Instead, if you have them like that, and you say somewhere either in the here or in basically in the text that you used Excel to and the average command to get the means, then that should be sufficient. If you want to, you can also give an example calculation. A way to motivate why you need to also motivate your choices of using means and dispersion units, for example standard deviations, would be something like to facilitate comparison between groups. The means and standard deviations were calculated using the average function and standard deviation stdev.s function in MX Excel. And that's going to be so hopefully sufficient enough to show that you use the correct type of technique here. And then you can write out what these means and standard deviations were in the text as well. So this is the kind of the level of detail that you should have when you describe it. So you don't describe the results in text. You don't need to have every individual data point, but potentially the range, but very importantly, the mean and standard deviations, if those are relevant. That would be useful. Thing like the means were 14.51, 34, 109, 175, and 234, 0, 20, 40, 60, 80, and 100% respectively. Something like that would be sufficient, plus these standard deviations. Then comes plotting the data. So you also want to make graphs of your data. I call them figures. I also, once again, recommend Microsoft Excel for doing this, because you make nicer, neater, more beautiful figures there. I also have, of course, videos for those as well, so I'll link those in the description too. Saying something that it allows for visual comparison and trend analysis is cool. You should always have figure legends below the figure, whereas you put table legends always above table. So that's an important distinction. Table legend above table, figure legend below figure. I don't know any mnemonic to be able to remember this. There are two common plots for you to use, bar plots and scatter plots. Others may be relevant as well. Bar plots are useful when your independent variable are categorical, so there's no numerical relationship. For example, site A, site B. Here we have an example from one of my students where they exposed asphalt with leaves for the urban heat island effect, and see how the temperature changed. So with leaves and without leaves were compared to each other. So bar plots are beautiful then. So then you should write that each of these the bars show the average increase. Here they didn't include that the error bars show standard deviations, would be nice. You need to have your, on the y-axis, you have your dependent variable with the unit, and on the x-axis, the axis title here should include the independent variable. Don't have any of these. That is not required. Now, if you instead have independent variable in numerical form, a scatter plot is more interesting, because you can make trend analysis then. And so here, once again, we have the dependent variable on the y-axis and the independent variable on the x-axis. And look how nice that is. Graph showing the mean invasion zones of E. coli by various concentrations of Manuka honey measured in millimeters. Nice. It could be added there that the averages, that you could include the number of replicates in here. Error bars are not described here either. Oh, that's bad. You can include the equation, and the r-squared value is also nice to have, because that's something we can use later to estimate in our evaluation. So that's cool. Now, apart from then reporting the data in text, in tables, and in graphs, we can do further techniques to process the data or analyze the data using statistical tests. Never mind. First, it was a dispersion, variation. This is something we also should do. So, standard deviations are common ways of showing or how the data varies. Standard error of the mean is also sometimes used, and that's basically the standard deviation divided by the number of observations, I think, if I'm not mistaken. So, standard error of the mean requires usually way more data points to calculate than standard deviations. So, don't worry about it. Use the standard deviations. Now, the problem of using standard deviations and be able to say, like, is this a lot of variation? Is it not a lot of variation? Is that it's not comparable to other studies. But there's a way to do that by standardizing your standard deviation. You do this by dividing the standard deviation with the mean value, and that gives you one version of what is called the coefficient of variation, and usually converted to 2%. So basically, standard deviation divided by mean multiplied by 100, then you get it to the unit of percent. And you can find some information about the coefficient of variation in many places. I'm going to refer you to some statistical websites later, and some of them will say that about 10 to 20% is usually low levels of variation. And these are important later when we talk about uncertainty in your data, so it's nice to calculate these ones. Now, finally, in the results section I'm going to refer to or deal with statistical tests. Now, statistical tests are important for you. That's going to also relate to your evaluation and your analysis, and also doing processing here. Usually, I would use to motivate. You need to basically describe why you chose these ones and so on. A nice way to do that is to say that statistical test allows us for objective measurements to analyze the data. So objective ways of finding patterns in the data. That is not us just looking at the tables and say, oh look, that looks different. That's pretty vague and subjective. So objective is much nicer. Reduces bias, and that's important for our evaluation. Now, there are some tests that you should be able to apply that you find in your skills section as well. There are two that are going to be useful for when we compare groups of values to each other, and that's going to be the t-tests and different types of t-tests, and the ANOVA. And for the ANOVA, also they recommend that you should know about the two key honest significance test, which is a follow-up test to the ANOVA. Then there's one that you should also know, which is called the chi-square test, which is used to compare ratios or something like that. It can be, but also to see if two variables are independent or dependent on each other. We'll talk about some examples where you can use the chi-square test soon. And correlation test, the Pearson correlation and the Spearman rank correlation. These are the ones that you should be able to apply. You need to justify which of the tests you chose, and you need to justify how it's applicable to the data that you have. I'll help you with those soon as well. And you need to explain why you're doing this test for this specific, what is the relevance for it, especially for your research question. I'll tell you some examples of this as well. And for each of these tests, you need to state the null hypothesis. That's called the H0. So this is the only case when we talk about the null hypothesis. All right, let's look at them one by one, or in groups at least. Comparing groups of values to each other. So we have the t-test. It comes in a few forms. We have the one sample t-test, and if you have one group of data points, and you want to compare them to one expected value. So you give them the range of data points you have, and you give the value to compare them to, and it gives you the p-value for. Actually, I don't know. There's no hypothesis for the one sample t-test. Well, you will find that later. It's not usually used. This is more commonly used, the two sample t-test. That's the one we tend to use. So for example, this data that I showed before in the bar plot here, that would be two sample t-test would be very applicable here. So comparing if this difference is basically, there's an objective reason to say that there's a difference between these two. Then a null hypothesis for the two sample t-test is that there's no difference between the means of these groups. So basically, whatever small difference that we find, we could expect by randomly sampling the same population. That there is basically in reality, if we assumed that we tested all possible surfaces covered and not covered with leaves, that we would then take a number of random samples there, and we would still be able to get differences, and we'll get different means in those. If we take two groups of samples from there, how likely is it we would get this type of difference that we've observed? So basically, null hypothesis, there's no difference between the groups, and it gives you the p-value for that, and that's something we're going to report. We'll talk about p-values soon. Repeated samples t-test can be used as well. So in my case, for the algae, that could be useful if I take the before data and after data. So this is what we call a dependent test. Two sample t-test assumes two independent groups that are not basically the same groups of data tested twice. Instead, can be seen as completely different. So I made two different samples. So if I tested the same group before and after they are dependent, then we need to have a repeated or dependent test, which is the repeated sample t-test. Then I can ask, is there a difference in the values in the before group, in before, compared to after? So that can be useful if I want to see growth in each of my specific temperatures. I could use a repeated sample t-test if I measured them before and at the start of the experiment, at the end of the experiment. But I would do a new one for each independent variable level, so before and after. Then I will be able to say, has there been growth in this group or not? ANOVA is very common, so we use that. That's basically the same as a two-sample t-test if you use it on two groups, but the ANOVA is cool that it can look at many groups at the same time. So if I have in my example with the algae, growing them in different temperatures, the ANOVA is very cool. I could do the ANOVA in the after data. So basically after I've incubated in these temperatures and see if there's a difference between any of the groups. So it will the p-value here, or the null hypothesis, is that there's no difference between any of the groups. And the ANOVA asks or tests or computes a little value that corresponds to the differences between the means of the groups. And the bigger the difference between those groups are, the lower the probability of the null hypothesis. Now, if there's any group that is different, we should follow this up with a 2-key honest significance test. And that will do all the pairwise combinations. So let's say I did my algae experiment. I cultured my algae in 20, 25, 30, 35, 40 degrees of Celsius. If the ANOVA gives a significant p-value, then it just tells me that at least one of the groups is different from the others. But it could be that all groups are different from each other as well. I don't know. But the 2-key honest significance test will do all the pairwise tests of like 20 to 25, 20 to 30, 30, 20 to 35, and 20 to 40, and then 25 to 30, 25 to 35, and 25 to 40, and then 30 to 35 and 40, and 35 to 40. Those are all the different combinations. And it's better. That's the better way of doing it. We could imagine that we do the two-sample t-tests repeated as well, and that's not going to be exactly the same, and it's going to make us more error-prone. So basically, ANOVA with the 2-key honest significance test would be nice. Now, I could do the ANOVA as well on my before data, if we're thinking about my algae experiment. But then, why am I doing this? So then I can explain why we want to motivate why we're doing this test. So in my experiment, I would of course like there to be no difference between the groups at the start experiment apart, so that otherwise I would have a bias. Basically, if I have a higher density in my 20 degrees temperature group, that would also impact how much algae I would have after a week of culturing them, right? So ideally, I don't want to have any difference at the start of the experiment, because then otherwise I have a bias. So that could be an important statement for why I'm doing this experiment or doing this test. To motivate why I'm doing the ANOVA at the end of the experiment will be like to be able to tell if there's been a difference in growth. I performed the ANOVA experiment, or ANOVA test, sorry. So that could be nice. So after that comes the chi-square test. This is the one I'm least familiar with, that I used at least myself. But there are two uses that I know that are relevant here. Basically, in ESS, it's not uncommon to do transect data, basically laying out, well, I shouldn't explain this now, I guess, that would be somewhere else. And maybe you're looking at 2 or more species, or their occurrences along the transect different from each other. So then the chi-square test would be useful. Comparing ratios, for example, if you're doing a germination experiment, and then you may not have many groups, maybe you don't have many groups in each, you basically have maybe 30, 40, 50 seeds, right, in each temperature, or whatever it is, and you want to see if there's a difference between those levels of the independent variable, then you should record the germinated and non-germinated seeds for each level of the independent variable, and you can compare those, like, are those the same or those ratios between germinated and non-germinated the same for each level of the independent variable. So then the chi-square test will be important. Now, correlation tests, those I would actually recommend that you do after an ANOVA or a chi-square test. Because if you don't have a significant, if you have replicates, that is, for your independent variable levels. If you just have like raw data that you can't really group into specific levels of your independent variable, then just go ahead with the correlation test. But if you have, for example, in my case, that I have 5 replicates of my algae per level of temperature, then at the end I want to do a correlation test as well. Then of course if the ANOVA doesn't tell me that there's a difference in the groups, why should I be looking at the correlation test? But if they are significant, then I think the correlation test is going to be important. I hope that I made that clear. So only if there's replicates, then you need to do ANOVA first or chi-squared first or something like that. Okay, there's 2 types of correlation tests. The Pearson correlation test is tests for a linear trend in the data. Reports an R value, which is the strength of the correlation. And this can be negative or positive. And the highest value is R1 or R-1. That means. And the second one is called Spearman's rank correlation test, and that gives each data point a rank value, basically highest or lowest. So if you have 5 data points, the ranks are 1, 2, 3, 4, 5 on both the dependent and independent variable scale, IV scale, and then it looks for how well these ranks follow each other. So basically, do we generally have increasing ranks on both dependent variable and independent variable? Then that tells us that there's some kind of relationship between them. Now, for performing these tests, some of them can be done on Microsoft Excel. If you have activated the analysis Toolpack, I have videos for how to do that as well, and videos of how to do many of these tests. Otherwise, I recommend these 2 web pages are very useful. SOCSTI Statistics, Social Science Statistics, and statscalculators.com. They're very useful for both these types of tests, and they also tell you a little bit about the p-values and the coefficient of variation and so on as well. You need to report the p-value of each of the tests that you performed. So the p-value represents an estimated probability of the null hypothesis explaining the data for each of them. That's kind of what the p-value test says, or is. That's p for probability. So that's why it's important to state the null hypothesis. And we commonly reject null hypotheses if the p-values are 0.05 or lower. And that's kind of usually what we want to do, except for if we wanted to say that there's no bias in our data at the start of the experiment, right? Then in that case, I wanted to have a higher p-value. I don't want to reject the null hypothesis. Cool. The teacher support material is a bit vague on what you need to report for the statistical tests. Sometimes they do suggest that you should also report what is called the critical value with the number of degrees of freedom that you have. So the critical value then is basically, so each of the tests calculate, or many of the tests at least, calculate a statistic value, a chi-square value, or a t-value for the t-test, or an F ratio for the ANOVA, and the degrees of freedom. Depending on the number of degrees of freedom, basically the t-value or F ratio that is needed to get a p-value lower than 0.05 is already given. So then they say you should report that for the number of degrees of freedom you have. I don't think that's going to be very, very important. I think the p-value should be sufficient, but yeah, that's a little bit of a bold move, I would be able to say. But both SOCSTI statistics, or at least SOCSTI statistics, will tell you report the critical value as well. And you should definitely report which software you use to perform the test. So write that you use SOCSTI Statistic, or write that you use MS Excel or something like that. That makes your processing you can ask if you did the processing correctly, and also it makes your whole method reproducible. And then write your interpretation of the test. What is this p-value that you got? What does it mean? Cool. I think that should be it for the result section. Hey, yay! And then we get to the discussion section. All right, the discussion has basically 2 criteria that we should fulfill, and these will come naturally after one of each other. So we'll start with the first one. Criterion E, that's the analysis and conclusion. So kind of the result section and the discussion, you kind of blend into each other to get the analysis. So I'd say potentially the statistical tests and so on that you did, those will be part of the analysis. And then the conclusion will be potentially the first part of the discussion. But to do all this, I suggest that you start your discussion section by restating your aim, research question, and any hypothesis that you have. Then you can give a summary of the data and your analysis of it, and support it by referring to the tables and figures and which statistical tests that you've used and what the p-values of those were. The teacher support material says this: the student must include a statement whether the data addresses the research question or not. So please do that. Now that you've given your summary of the data and your analysis of it, you basically get automatically an answer to your research question, and that should be the conclusion. Now it says specifically here, the analysis, the conclusion addresses the research question is supported by the analysis presented. So you can make your conclusion be very vague. So in case or a bit vaguer basically, or simpler. So for example, let's assume in my experiment with the algae in different temperatures that we saw lower algae densities at higher concentrations. So it could be something like that. That with higher concentration or higher temperatures, the algae densities drop or decreased. And then basically that could be my conclusion. Now, if I saw that the pattern was not completely linear all the way around, maybe they went down to 0 already at 30 degrees and then 35 and 40, there's no change. Then a more subtle conclusion would be that would include this information, right? So it would say something like the algae density decreased in higher temperatures, but after 30 degrees there was no further decrease in algae density or something like that. Or so that would be a way to make sure that all the patterns that you find in your data actually is in your conclusion as well. So it makes the conclusion a bit more interesting, a little bit more more complex. But of course not. We shouldn't make it complex for the sake of complexity, but it should be explaining all the data that I have. And here we see also the little text to accompany what I just. All right, and for the first strand, the analysis describes patterns or trend, and it includes some measures of bias, reliability, validity, and uncertainty. Oof, this is a mouthful of stuff, isn't it? So let's kind of figure out what those kind of things are. So the first thing I'm going to talk about is not actually in here. Errors. Errors are basically, in measurements, there are differences between what is called the true value and the measured value. So if I'm going to measure the temperature in the room, there's a true temperature in the room, and then when I measure with some instrument, I may or may not get that exact value. Now, for most cases, we don't know what the true value is, of course. But there are 2 types of errors that I can make now in my measurements. Either I make a systematic error that I'm always measuring lower or higher values than the true value, or that I'm measuring both above and below. Those are more random errors. Uncertainty is basically relates to these errors, so it's a bit more vague here. It's a possible value an error might have. That's the definition of uncertainty. And once the same here, we can have systematic or measurement uncertainty, and we can have random uncertainty. So we have uncertainty in here, so that's actually something in the mark strand, so that's nice. Measurement uncertainty relates basically, or most relevantly at least, to the precision of the instruments that we've used in our experiment. Whereas random uncertainty are basically fluctuations in environment or in experimental conditions that would lead to kind of random errors, right, or random uncertainty. Or there's also intrinsic or individual variability that has a large effect. So in biology and ESS, the intrinsic variability is very important. How do we deal with these uncertainties? Making sure that our measuring device has the accuracy or sensitivity that is correct for the type of data that you want to measure, that it can accurately detect the differences that are relevant to us. That's going to be important. So I'm not using a light microscope to be able to see viruses or something like that. That would be the wrong measuring device for this. Or if I'm using a scale that has an uncertainty of sensitivity of 0.01 grams, and I'm trying to weigh something that is lower than that, or that varies from each other lower than that, then we're not gonna be having the right kind of equipment, right? So basically, to deal with this, you need to report the measuring uncertainty and discuss if it's relevant for your conclusion. Basically, the patterns that you have or the difference that you see in means or something like that much bigger than the measuring uncertainty of the equipment, then that's cool. Making sure that you've calibrated all your equipment is going to be important for like pH probes or something like that. Nitrate probes, that calibration was recent, that it was done correctly. Statistical tests also account for uncertainty. So random uncertainties give standard deviation and so on. Variance in the data. Statistical tests will account for those. Will be an objective way to ascertain if those have an impact or not. When it comes to scatter plots, R2 values that are like the coefficient of determination is what the R squared value, did I say R2? I was just wearing an R2D2 shirt yesterday, so maybe that's why. But R squared is basically how well your mathematical model captures the variation in the data. So if you have a scatter plot and you report the R squared value, that will tell you how well the data follows the pattern of the linear trend or whatever trend you've added there. So that is also an important value to use to deal with uncertainties. So if that's, once again, R squared values can also change from 0 to 1, because you square the R value for a Pearson's and you get the R squared value. So squaring a negative value gives you positive value. So squaring -1 gives you 1. Basically, so that's tells us how well the data follows the linear pattern we have. Do we have sufficient number of replicates? That will be uncertainties. So the standard deviation and so on are also uncertainties in our data. So coefficient of variation. So reporting those is also going to be very important. Second one, reliability, is the degree to which we get consistent results each time we perform the same measurement or experiment. So if I repeat this data, would I get basically the same, would I be able to draw the same conclusion then my experiment has high reliability. And usually, reliability, oh my god, it's been over an hour now, so maybe that's why I'm starting to have some problem enunciating, can be assessed by having many replicates or repeating the experiment. So having many replicates, we can see if our reliability is high or low. If we repeat the experiment and get the same results, then that tells us that our reliability is high. So the measures to assess reliability, if we have many replicates, will be low dispersion values or variation values, so low coefficient of variation, or high values on our R squared trend line would be nice as well. And generally we have a low reliability if random errors are high, fluctuations in the environment or experimental conditions. So if I have also low control variables, then that's going to be, or low control of confounding variables or control variables, that's going to make random errors high, and few individuals then, or low replicates, then the individual variability will have a large effect. Validity is basically how well your project, research question, experiment tests your aim and hypothesis, for singular. Sometimes this validity is broken down into two different types of validity: internal validity, and that is going to be the strength of any causal relationship that you can determine. And external validity is how well you can generalize the results that you have. For example, if I wanted to test a medicine and see what effect it has, maybe I'm using a mouse model, and that will give me high internal validity. because I can control stuff, control the variables that I need to be able to draw a causal relationship. But if I'm going to say something about how that applies to humans, then my external validity might be low. But if I instead test on humans, I might have the opposite thing, that I have really high external validity, but since I can control for the same confounding variables by having, for example, genetic copy or clones of everything to test this, then I have lower internal validity. Validity can also be seen in the procedure, or here, validity instead of validity. Basically, control of confounding variables gives you higher validity of procedure. Using correct dependent variable to be able to test your aim, and if you have sufficient data to determine reliability. If you have low reliability, you will also automatically have low validity. Validity in analysis, that's using appropriate methods for analysis. Am I using the right types of statistical tests to be able to define the patterns? Validity can be assessed by the accuracy, which is another method or another measurement. Is basically, am I getting the expected results? If I have low errors, I have high accuracy, and then I automatically also have high validity. And the teacher support material kind of hints to this being something you can use to determine validity as well, insofar as you would be able to look for, if you compare your conclusions to other studies done on something similar, are they getting the same results? Are they seeing inhibition at the same similar levels of the independent variable that you have for different systems or something like that? Are you seeing the patterns that you expect to see from theory that also can do this? So basically use references here to compare your results to be able to say if you have found something reasonable or not. That will be one way of looking at if you have high validity. Bias causes distortions in the results and wrong conclusion. Biases are always there, so that's something to be aware of. Biases can be seen in many different levels. Measurements bias, that's when we're measuring key variables inaccurately. We have a survey with the wrong questions, so that will reduce validity. Or the subjects are self-reporting. There's an interesting study or contrasting studies of people either self-reporting the length of their penis when erect, compared to if the scientists are measuring the penises, then the world average drops by 1 centimeter, I think, if it's the researchers doing the measuring compared to if subjects self-report. I wonder why. Then there's observer bias by the subjects or observers are basically skewed, not reporting what actually happened because of our perspectives being influencing this. Researcher bias, that's basically when the scientists themselves basically cherry pick among their own data or how they interpret the data or how they design their experiment so that they get bias. Or sampling, basically, if I measure the population, I put the subjects in the different groups, either so they don't represent the population in general, or that I put parts of or different subsections of the population in the different groups. So maybe my control group would have all the weak or strong individuals or something like that, or only males versus females or something like that. Only males in the control group, only females in the test group. Then it's like, oh, then I'm biasing my results already at sampling stage. And that last one relates to my talk about using the ANOVA on my before data, for example. That will tell me if I've done some sampling bias, for example. If my initial conditions, there's no difference between them, then I don't have any of these selection bias. So that was some kind of connection back to what we talked about. Cool. So those things are that you can kind of relate to in here in your analysis and conclusion. Some of this will come back also in the last criteria, which is the evaluation section. So this one talks about limitations and weaknesses that impact the conclusion. The highest points are given for evaluating specific limitations or weaknesses and evaluating improvements and describing unresolved questions. There's no formal need to distinguish between what's a limitation and what's a weakness, what those terms are. You just need to, you can bunch them together. But basically, methodological weakness include control of variables and precision of measurements, and limitations may include like the range of the independent variable, number of duplicates, and the choice of study species. That can introduce limitations. So to score high, you need to both describe and evaluate them and suggested improvements. What do those things mean? So describe means that you give a detailed account. Evaluate means that you make an appraisal, so make judgments about your about how much they impact the conclusion. So what they suggest here is that you at least say something about this weakness has a minor effect or a major effect, but you need to give the reasons for why you think so as well. And this is very important, or very commonly not done. A lot of students end up outlining or describing weaknesses, but not evaluating them. This is tricky, but can be done. Let's give some ways how to do this. So you should use for variation in the data. So this relates to reliability. If the reliability is low, then that should be telling us that there is some limitations or weaknesses going on. So these standard deviations, coefficient of variation, use them to judge random uncertainties, and that gives us some weaknesses, right? You can use your measurement uncertainties to judge the degree of impact from measurements. You can use trials and pilot experiments as well to help doing this, and calibration to be able to determine if you have the right types of equipment, right? You can discuss when and how the data was collected. For example, if you're doing some kind of impact, if you're measuring something in a river or other place, right? If there's rainfall that will that have happened recently, that will impact the levels of pollutant in the river, or the season will impact the amount of biodiversity you'll see, things like that. For our algae culture, if you've stirred them before or after, that will impact how well we have homogeneous sample to homogeneous samples that we can compare. If you've introduced cold thermometer into warm water, that will change the temperature of the water. Things like this can be used in the evaluation here. Surveys, if you use surveys, you will have a selection bias because there's involuntary or voluntary participation, I hope, which introduces bias. And people tend to avoid extreme answers if you use like a Likert scale. And if you have really long surveys, you will have survey fatigue and so on. So this kind of relates all the way back to this measures of validity and reliability. If you have talked about those already, you already kind of start getting information that you can use here for the evaluation as well. A nice way to structure this is to make, once again, a table. The first column of that table will include the description and evaluation of the limitation, and the second column will have the improvement. And you need to evaluate the improvement as well. So doing this thing instead, and you need to motivate if that has a major or minor impact and how it impacts the strength of your conclusion, right? So this one is potentially one of the tricky ones, but you cannot basically get the 5 or 6 marks here if you don't do the evaluation. So just practice doing evaluation. Ask your teacher for feedback on this. But yeah, it's going to be important. The final thing is going to be unresolved questions. So basically, after this table, I would put then at the end of the discussion section. So the discussion section started first with the conclusion, and then the second half here with the evaluation. And at the very end, we state our unresolved questions. And these should relate to the conclusions you're trying to make for your project, so relate to the same aim, but they need to be different, extend upon what you've already done. And these suggestions should be then potentially some kind of new research question to be able to get more information, to be able to draw a stronger conclusion or extend your conclusion. It needs to be realistic, means that they should have the same limitations as your IA, so 10 hours of work. That's the same thing with the improvements. They should be realistic, meaning that they should be able to be done with the in the same limitations as the IA. Relate to the same environmental issue should go beyond the original method and enhance the understanding. That could be that for the same study system, you use a different dependent variable, or you use a slight variation of the independent variable. You use a different field site, different season, or investigate the impact of one of your control variables in the same system. Those are ways to kind of inform your unresolved questions. Whew. And that's the end. 1.5 hours. Oh my god. I hope you make it to the very end. Good luck, everybody.